If oil is spilled from a tanker, the area in the oil slick will grow with time. Suppose the oil slick is always a perfect circle. In practice, this does not happen because of the winds and tides and the location of the coastline. The area of the slick is a function of its radius. This function is A equals pi r squared. The radius is also a function of time because the radius increases as more oil spills. Thus, the area, being a function of the radius, is also a function of time. If, for example, the radius is given by the function g of t equals 1 plus t, then the area is given by substitution. So this is where our composition of functions come in. So if we wanted to compose a new function where it was just the area in terms of the time, we would have to substitute the function that represents the radius into our area function. So our new function would be a of t equals pi, where the radius is, we substitute in 1 plus t squared. This is composition of functions. So you remember learning about this in Math 3. Whenever we see f of g of x, that means to substitute the g function into the f function. Be careful, this little O right here is the symbol for of, not times. All right, so given the function f of x equals x squared and g of x equals x plus 1, we're going to figure out what f of g of 2 is. So in other words, what is the range value when the domain value is 2? So to do that, we have f of g of 2. I'm just going to rewrite this using some colors so y'all can see the composition happening. So that is saying f of, and we're going to evaluate the g function for when x is 2. So that would be 2 plus 1. And obviously 2 plus 1 is 3. So that gives us f of 3. Now that we have cleaned that part up, now we're going to go to the f function and substitute 3. So when we do that, that gives us 3 squared, which would ultimately be 9. So what that means is on this new function f of g of x, when x is 2, y is 9. All right, y'all try b. Okay, so in this case, we're going to substitute 2 into the f function, and then whatever we get for that range value, substitute that back into the f function again. So f of 2, that means to find out what 2 squared is, and we know that 2 squared is 4. So then this turns out to give us f of 4. So now we're going to substitute 4 into x squared, so that would be 4 squared, which is ultimately 16. So therefore, f of 2 is equal to 16. When x is 2, y is 16. Now let's do it for the actual functions. So let's say we're going to figure out what the function f of g of x is. So if we substitute g of x into the f function, since g of x is equal to x plus 1, we're going to replace g of x with x plus 1. Now we're going to go to our f function where we see x, we're going to replace x with x plus 1. So our new function is that f of g of x is equal to x plus 1 quantity squared. We could also write this as x squared plus 2x plus 1. If you want to test out the problem above where we did f of g of 2, if we were to now take this new function we created and substitute 2 into the function, so f of g of 2, that would have been 2 plus 1 squared, which would ultimately have given us 9, which checks out with what we did above. So you can either work your way inside out when doing the numbers, or you can find the function and then substitute the numbers in. All right, now let's look over here at g of f of x. So this is the opposite. In this case, we're going to substitute the f function into the g function. So since our f function is x squared, we're going to go over to our g function, and where we see x, we're going to replace it with x squared. So this ultimately gives us x squared plus 1. Notice that f of g of x and g of f of x are not the same function. They are different functions. All right, so let's talk about the domain of f of g. The domain of f of g must be a subset of the domain of g, the inner function. This is a really important concept. When you are doing this, because you start with the inside function, you have to be within the domain of whatever that function is. Even if once you apply the outside function, it has a domain of all real numbers, or it cancels out the domain that you had to start with, you still have to stay within the domain of the original function. So this is really, really important. So we're going to do some more of these where we do the composition and we state the domain. Okay, so the first thing we want to do on these problems is figure out the domain for each function before we get started. So for the first one, it's just a quadratic function that has a domain of all real numbers. However, the second one is a square root function. Sorry, y'all. Sorry about that. Let me put that down. All right, the second one is a square root function, so we know that whatever's inside the square root cannot be negative. Therefore, if we take x minus 5, set it greater than or equal to 0, that tells us that the domain for this must be x is greater than or equal to 5. All right, so now let's do their composition. We'll start up with f of g of x. So for f of g of x, that means that we are substituting the g function inside the f function. And the g function is equivalent to the square root of x minus 5. So then, once we substitute that into the f function, so where we see x, we replace x with the square root of x minus 5, and then we would square that plus 3. So when we square a square root, we know they cancel each other out, so that gives us x minus 5 plus 3. Therefore, we get the function x minus 2. So f of g of x is equal to x minus 2. If we only looked at this function, we would think that the domain was all real numbers because that's a linear function. However, since the inner function was the g function and it has a restriction on the domain, we have to be within that domain. So our domain for this function is going to be from 5 to infinity, including 5. All right, so now let's do the opposite. Now we're going to find g of f. So that means we are going to substitute the f function into the g function. So we're going to substitute x squared plus 3 inside of g. So that is equal to the square root of x squared plus 3 minus 5. So when we clean that up, that gives us the square root of x squared minus 2. And folks, that's as far as you can go. You cannot take the square root of just x squared. The only way you would be able to take the square root of that expression is if you were to factor it and it had two equal factors, which it clearly does not. So to figure out the domain for this one, when we started, the domain was all real numbers. However, now that we've created the function, we've added some restrictions because we have an even radical. So we have to figure out what is the domain for this part. So we come over to the side, x squared minus 2 must be greater than or equal to 0. If we find the zeros for that, that's x squared minus 2 equals 0, which gives us x squared equals 2. Therefore, when we take the square root of each side, we get that the zeros are x equals plus or minus the square root of 2. We would draw our number line, put those roots on our number line, negative square root of 2, positive square root of 2. Because this is a parabola that opens upward, and we want to know when it's greater than or equal to 0, we would shade on the outsides, including those zeros, because it can equal those numbers. Since our inner domain was all real numbers, we just add this to that. It has to be within that. So our domain of the g of x function is going to be from negative infinity to negative square root of 2, bracket, in union with, bracket, the square root of 2 to infinity. So understand, that's why we say that the domain is a subset of the domain of G. You have to be within that domain, but if you add more restrictions when you create your function, you've got to add those restrictions to the inner function's domain. All right, why don't you pause the video and try the next one, then play back the video to see if you're getting it correct. All right, so since f of x is an exponential function, we know that the domain for all exponential functions is all real numbers. However, g of x has a logarithmic function in it, so we know that the domain in this case is x is greater than or equal to, x is greater than 0. It cannot equal 0. So in other words, it's from 0 to infinity. So let's start with f of g of x. So we're going to substitute this g of x function into the f of x function. So that is going to give us e raised to, and here's where the g part comes in for x. So the natural log of x plus the natural log of 3 minus 3. Let's see if we can try to clean this up a little bit. Using our property of logarithms, we know that that is saying e raised to the natural log of x plus the natural log of 3. If we multiply those together, would be the natural log of 3x. Then we still have this minus 3. We can actually use exponent rules and simplify this further from here. We could say that this is e to the natural log of 3x times e to the negative 3 power. Because remember, when we multiply like bases, we add the exponent, so we could always break up an addition or subtraction with the multiplication. By doing this, we can now apply our inverse property. E raised to the natural log of 3x gives us just 3x. And then we still have times e to the negative 3. And if we really want to clean this up, then that would give us that f of g of x is equal to 3x divided by e cubed, because we know we normally do not leave negative exponents in our final answer. Guys, remember, e is just a number, so therefore e cubed is just a number. So really, when we're done doing this, this is just a linear equation, because the coefficient is 3 divided by e cubed times x. So we did not create any new restrictions in here. However, since the domain of the inner function is from 0 to infinity, the domain of this function has to remain 0 to infinity. All right, now let's do g of f of x. So we're now going to substitute the f function inside our g function. So we're going to have the natural log, there's our x, so that's where we're going to replace that with e raised to the x minus 3 plus the natural log of 3. In this case, it's a little simpler because we can immediately take that power of x minus 3 and drop it down in front. So this is going to give us x minus 3 times the natural log of e, which we know to be just 1, or you could have just used the property of the fact that anytime you have natural log of e raised to a power, it is just that power. And then we still have plus the natural log of 3. So ultimately, this is x minus 3 plus the natural log of 3. Again, in this case, we've ended up with just a linear equation because negative 3 plus the natural log of 3 is just a number, as ugly as this may be. And since the inner function had a domain of all real numbers, and our new function hasn't created any restrictions on the domain of this function, g of f of x, is going to be all real numbers. Okay, so we've created functions using new functions using the actual functions. Now let's do it using tables. So we're going to start out pretty easy. What is f of 3? We go to the table of f of x, we look when x is 3, and we can see that y is 1. Therefore, f of 3 is equal to 1. Now when it says what is g of f of 3, since we already know that f of 3 is 1, we will now say, well, then this is equal to g of 1. So we go to the g function, we look when x is 1 and y is 4. So therefore, this is equal to 4. Let's look at the next one. What is g of 3? If we look at the g table, we can see that when x is 3, y is 2. So now it says, what is f of g of 3? So since we know that g of 3 is 2, we're going to substitute that in there. Now we will go over to our f table, look when x is 2 and y is equal to 2. So therefore, f of g of 3 is 2. Again, notice that g of f of 3 and f of g of 3 are not the same. So we've worked on composing functions. Now let's discuss decomposing functions. So this is the exact opposite of composing. In order to decompose a function, we need to be able to recognize the inner and outer parts of the composite function. So given f of g of x equals the square root of 5x minus 3, find f of x and g of x. Notice g of x is the inner function, so you're trying to look for a function inside another function. Do not let x be the inner function. It needs to have something other than just x. So when I look at this, what I see is that 5x minus 3 is inside that square root. So one way we could do this is we could say, okay, the inner function is 5x minus 3. What did we substitute that into? We substituted that into the square root of x. And always check it to make sure it works. If we were to take 5x minus 3 and substitute it in for x, we would get the square root of 5x minus 3. This is one possibility. We could have also said, well, I see 5x inside. So you could have also had g of x is equal to 5x. If we did it that way, what did we substitute that into to get the square root of 5x minus 3? We would have had to have substituted that into the square root of x minus 3. This would also work. Whenever you are decomposing functions, make sure to check it and see if you were to compose that back, it would give you the original function. All right, pause the video and try the next one. Okay, two options you could have had was that the inner function was 4x squared and the outer function is x minus 1, or the inner function is x squared and the outer function is 4x minus 1. I always have students think that this works, so let's look at this real quick. What if you thought the inner function was 4x and that the outer function was x squared minus 1? This is why you should actually check it and compose your function back. If we were to substitute 4x in for x, that would have given us 4x squared minus 1. And when we clean that up, that would have been 16x squared minus 1, which is not equivalent to 4x squared minus 1. So when we decompose functions, always check them. All right, last part of our lesson, definition of inverse functions. We've been talking about inverse functions here and there over the last couple of weeks. So now we're going to go back through it for all inverses of all functions. All right, so starting out, two functions, f and g, are inverse functions if and only if f of g of x equals x for all the x in the domain of g, and g of f of x equals x for all the x in the domain of f. Guys, this is the definition of inverse functions. When you substitute a function into its inverse function, and vice versa, they undo each other. That is why when we do their composition, they will strip each other down so that all we have left is x. This is the only time when you compose f of g of x and g of f of x that they will be the same. If you compose f of g of x and g of f of x and they come out to both equal x, they are both the same, it is because they are inverse functions. All right, properties of inverse functions. Given that f and the inverse of f are inverse functions, then f of a equals b if and only if the inverse of f of b equals a. Pretty much what this is saying is if you have the point AB on the original function, you have to have the point BA on its inverse function. That's the whole point of inverses. The domain becomes the range becomes the domain. Okay, existence of functions. A function will have an inverse function if and only if it is a one-to-one function. If it is a one-to-one function, we say it is if it is not a one-to-one function. Okay, let's look at the function y equals x squared. If we look at the graph of this function, we can see that it is a function, but it is not a one-to-one function because it does not pass the horizontal line test. For example, if we look at the y value of 4, it has two x values paired with it. It has the x value of 2 and the x value of negative 2. If we were to find its inverse, we would switch x and y, so we get x equals y squared, and then solve for y. So we would take the square root of each side, which would ultimately give us plus or minus the square root of x is equal to y. So therefore, we are saying that the inverse of this function is plus or minus the square root of x. What happens is that graphs the positive square root of x and the negative square root of x. So we can clearly see that the inverse of y equals x squared is not a function. It is an inverse relation, but not a function. So sometimes what we have to do in order to make a function have an inverse that is also a function, we have to restrict its domain. So for example, if we talked about y equals x squared, and we restricted the domain to be from 0 to infinity, then its inverse would be the positive square root of x. So because that way its range would be from 0 to infinity. Or vice versa, if we did y equals x squared, and we talked about the domain from negative infinity to 0, when we did its inverse, it would be the negative square root of x, because the range of the negative square root of x is from negative infinity to 0. Remember, the domain of the original function should be equivalent to the range of its inverse function. All right, so let's look at the rule of 4 for inverse functions. And remember, this is something you need to be doing in your portfolios. So let's use the example f of x equals x cubed plus 1. Let's start out with doing the algebraic part, actually finding the inverse. So every time I do this, I normally take the functional notation out to start with. So I just say, okay, let's say we've got y equals x cubed plus 1. The first step in finding any inverse is to switch x and y. So we'd have x equals y cubed plus 1. Then we would solve for y. So we would subtract 1 from each side, x minus 1 equals y cubed, and then take the cube root of each side. So ultimately, we get that the inverse of f of x is equal to the cube root of x minus 1. All right, the other algebraic piece for inverses is proving that two functions are inverse functions. To prove that two functions are inverse functions, we need to do their composition. So when you do this, make sure you do it both ways. So let's say we start out with f of the inverse of f of x. So what that means is we're going to take our inverse function and substitute it into our original function. So it would look like this. The cube root of x minus 1 substituted into x cubed plus 1. In other words, we replace x with the cube root of x minus 1. When we cube a cube root, they undo each other, so that x minus 1 would just pop out, and we still have plus 1, which ultimately would equal x, which is what we wanted. But that's not good enough. That's only one side of it. You have to do it both ways when doing this proof. So then we would do the inverse of f of x. So now what we're going to do is take the original function and substitute it into the inverse function. So this would be the cube root of x minus 1, but where we see x, we're going to substitute x cubed plus 1 minus 1. So then we can see that that positive 1 and negative 1 cancel out. We would have to do that part first. So we have the cube root of x cubed, and then of course the cube root of x cubed equals x. And you can see that in both cases they stripped each other down. In other words, they undo each other. That's what inverses do. That's the whole point of them. All right, let's look over here at the verbal piece. So verbally, to find an inverse, number 1, we switch x and y. 2, solve for y. To prove two functions are inverses, do their composition of each other. One-to-one functions. Remember, in order for a function to be one-to-one, it must pass the vertical line test and the horizontal line test. So if you think about what the graph of y equals x cubed plus 1 looks like, we know that's a one-to-one function. Also, remember, inverse functions should reflect over y equals x. Even if they're not functions, even if they're just inverses, they always reflect over y equals x. All right, so let's look at this numerically and graphically. All right, if we're looking at the original function, f of x equals x cubed plus 1. That's our basic cubic function shifted up 1 unit on the y-axis. So that function would look like this. So pretend like you're at the origin. We go out 1, up 1, out 2, up 8. Then we would go back 1, down 1, back 2, down 8. So this cube root function would look like this. Let's write down some of those points real quick. So we would have had the point 0, 1, 1, 2, 2, 9, negative 1, 0, negative 2, negative 7. All right, so remember, for every point AB, we have the inverse point BA. So now, let's use our knowledge of cube root functions and graph the cube root function we created, which was the cube root of x minus 1. We know that that function would shift right 1, and then we would graph our cube root function. So if we pretend we're at the origin, we go right 1, up 1, right 8, up 2. Or we go back 1, down 1, back 8, down 2. And so if we write down some of those points, on our inverse function, we have the points negative 7, negative 2, 0, negative 1, 1, 0, 2, 1, 9, 2. And what we can see is all the points on the original function, we have the inverse points on the inverse function. Guys, this is really important to be able to look at the rule of 4. Let's say you're doing a problem on a test or a quiz on your exam, and maybe you can't figure out the inverses algebraically. Could you look at their tables and do them numerically? Could you look at their graphs? Are they reflecting over the line y equals x? Could you use the definition and see which ones would undo each other when you did the f of the inverse of f or the inverse of f of f? You should be able to look at this for all ways. And then make sure you always graph the line y equals x and that your function reflects over that line y equals x. All right, note, again, not all functions are invertible. They must be 1-to-1 to be invertible. So that means if you're going to find an inverse of a function and you want that inverse to be a function, make sure it's 1-to-1 first. Here's a little way to test if a function is even, odd, or an inverse altogether. If you're given any point, let's say it's the point xy. If it's an even function, it will have the point negative xy. If it's an odd function, it will have the point negative x, negative y. If it's an inverse function, it'll have the point yx. All right, so now you are to complete the practice on the next page, and we will go over this on Monday.